will be helpful in building animations. These are all tools you have in your toolbox, and we'll continue to build on this list. But it's just good to kind of summarize and recall things that we've talked about that are going to be really helpful. So, share my screen. Okay, so here we go. So the first thing is defining functions and using function notation. Right? Function notation, super convenient, especially when your expressions start getting bigger and bigger, and they're building on other functions, right? Or you have functions that build on other functions. So I meant to show you an example of this that we're gonna be building up to, which is the approximate accumulation function. And within that function, there is multiple uses of other functions, and then so the function notation is kind of necessity. We got to have that. All right. Free variables in GC as parameters, variables, function names, constants. Okay. So we know that there are some. Let's see. So there are some things that are reserved. So the most common ones are n, x, y, t, pi, e. Those are kind of the most common ones that are reserved. Lowercase u and v are reserved. R is reserved. Let's make sure we got the full list of the common ones here. So R, what do they say? U and V. Any others you can think of that are we come across often that are reserved symbols?
Is theta reserved?
Theta is reserved, but to get that you type in theta. So you have to type in all the letters. So that's not really a danger. One that it's not a single symbol when you type it in.
What are U and V reserved for?
They're like for vector functions, parametric functions of two variables. So they're similar to t. So like when you can write a surface, if you guys remember from Calc 3, you can write a surface with two parameters as a vector function. And that's not that. It should be this. And so the conventional nomenclature there is for those two parameters are u and v. So that's what GC has that also. Anything else you can think of?
Fine Z.
What's that? Oh, Z, right. Z, yeah. If you type in Z, that's going to open an R3 axis. So yeah. All right, next one. Okay, so this I want to show you. After we get through the list, we have not done this yet, but there's a couple things on the list we haven't talked about yet. This is one of them that I want to show you. Repeated elements with a parameter and a set of values. So I'm going to show you that. So put that on hold for a second. Here's another thing I have not shown you yet, which I will show you right after we get done with the list, and that is piecewise functions. Use Control A to add new pieces to a function. We'll explore that a little bit. Okay, but this we have definitely done. So graphing functions including over intervals, graphing lines, graphing points. We saw absolute value gives us not just a V shape, but any kind of reflection. We can use absolute value to get a reflection. And then graphing regions, right? Graphing regions, we had the heart and kite homework. And so that's all important stuff there. And then we talked last week ago about the morphing operator. And I showed you this is an extremely powerful tool. So you have to remember exactly what this is and remember that it can come into use a lot. It's very helpful. But if you kind of just have a hazy recollection of it, then it will never come to mind as something you can use. So I'll show you some more examples after we get done with this list. I'm going to show you a couple more examples of how I've used that, or one in particular. Animating with sliders. Okay, so not only the n slider, but then I showed you how you can use your free variables to make more sliders up in the math lines. Okay, and then view sliders, right? So these are the same exact type of sliders, but we can use them for turning on and off objects with if-then statements in the math lines. So if, plot this point, if, if view equals 3. Plot this region if view is less than or equal to 2. And then you can have that view slider just set for integer values, and you can manipulate the view slider, and then you can have things turning on and off. So that's use that all the time in the animations that I've built. Okay, and then constant rate of change, and then we worked hard on the point rate form of a line, which was this. Given some point and given the rate of change, we started with the change in x, used the constant rate of change to write the change in y, and then we write initial y plus the change in y gives us a final y, which kind of represents like every y value on the line. Okay, so I promised you 3 things here. So let's talk about repeated elements, piecewise functions, and I'll give you one more example of the morphing operator just to get it into the forefront of your thinking. This morphing operator is super helpful in building animations. Any questions on this list? Or comments, observations? Okay, so let's talk about repeated elements. I'm going to open up a new GC file here.
Are you recording this?
I am.
All right.
Okay, so so repeated elements. So you can do something here where suppose I want to graph something over and over and over again, like a line segment. I want to graph a line segment over and over and over again, but I don't want to, I don't want to do one math line for every one. So say I have, maybe I have 50 of them. So let's do some tick marks around the unit circle. So how can I plot the unit circle here? What should I type in to plot the unit circle? Anybody? Anyone know the equation of the unit circle?
Guess I'll do it. X squared plus y squared equals 1.
Richard saves us here. Okay, there it is. Zoom in a little bit. So suppose I want to put tick marks for every 10 degrees. All right, so I want to make a little line segment on this every 10 degrees all the way around the circle. So what is that? How many is that? 36 tick marks. And I don't want to make 36 math lines, right? So I can do this all in one line. Okay, I can do this all in one line. And so what I can do is, so I want to write what's like a typical tick mark on the unit circle. So I don't want to use x and y, I want to use r and theta. Right? So how can I write a little line segment in terms of r and theta? So I'll draw it and then we'll see if we can come up with it. So suppose I want to draw a segment like that, say at 27 degrees. Okay? And I wanted to, just draw that thing right there. How could we do that? So remember that in R2, we've got R and theta are reserved for their typical meanings as variables in R2. Anyone? So what will the kind of the structure of that math line be? So what defines a tick mark? So what's true? What's true about that? Like, you know, like how do you draw a vertical line? How do we draw a vertical line? What would a GC do for that? How would you, in GC, how would you draw a vertical line?
You would just type like x equals whatever the value is.
Yes. Why? Because now it's going to graph every point that has that x value, and that's a vertical line, right? Can I use something the same for this? I want to do a tick mark at 27 degrees.
Would you like find the equation of that line and then just restrict your domain?
Yeah, but then now you're gonna bring x and y into it, and then like every single one is going to be different. So that's not the way to go here. But okay, good idea. At least we're getting started. So the nice thing about a vertical line is do you have a constant that defines it, right? X equals 2.6. Do you have the same thing here?
You have an angle.
Okay.
That defines it, maybe.
Yeah, there are all these points for a constant angle. And if so, what angle?
27.
27? 27 degrees. So I could theta equals, we do 27. Now it's expecting radians, so what?
Times pi over 180.
What are we going to see for that? So what's that going to do?
It should make just like a straight line from the origin all the way for all the points that.
It's going to plot every point associated with this angle measure. Oh, look, that was a good guess, right? I pulled 27 out of the hat there. That's good. I get a cookie. Okay, so but that's okay. So and then that's showing it what r from 0 to, so down here. Can you see the bottom of my screen there where I'm circling? Or is that too low?
You can see it.
Okay, cool. So notice it's showing all the points from 0. As soon as I put theta in, it's in polar mode. It's showing everything from 0 to 2. So what do we want? So we've done this before. So this is similar to what we've done before, and we're just doing it in polar coordinates instead of x and y coordinates. So what do I want? I just want a little tick mark here, right? How can I do it?
Angel, I thought you were going to say it. I'm pretty sure you know what it is.
But what's the difference between this whole line from here to here and a little segment from there to there? Mathematically, what's different? So we just got to specify the mathematics for a little tick mark rather than the whole thing. Ashley, any idea?
If r is from 0 to 2, maybe like restrict the domain of r.
Okay. From what to what?
If you just want to tick, I'm not sure, like 0.9 to 1.1, or I'm not sure.
Well, just try it and let's see if it looks good for us. Take that off. What do we think? You guys like the size of that? Is it good? Sure. Okay. So now I want to do this. I want to do a bunch of these every 10 degrees all the way around. Okay, so rather than do 27, I'll just do a parameter, say A. That'll be my degree measure. And then what I want is, now I want to specify that A is from a set of elements. And it'll take every element in the set, and it'll plug it in there and repeat this for every element of A in the set. So you can do, on Mac, it's Control equal. I'm not sure about a PC. You can try that. And then when you use the set notation, which is shift square bracket to get the curly brackets. And so what do I want A to be? I said I want it every 10, right? So I can do 0, then 10. Now I could sit here and I could type out the whole list, 20, 30, 40, and that would certainly be easier than 36 math lines. But there's even an easier thing I can do. You can start the pattern and then do control semicolon, and it does a dot, dot, dot. And then what's the last one that I want? I've already got one at 0. So if I'm doing every 10 degrees, then the last one I want is?
360.
So I've already got 0. So I could do 360. It'll repeat it though. So see, that'll be in the same place as 0. So you see I can do 350. All right. So now what will this do? It'll, for every value A from for every value A starting at 0 to 350, it's going to plug it in there and plot them all, right? So it's going to plot all of them simultaneously. What happened? It tried. We did something wrong. What did we do wrong? I think it's because you only do the first. Yeah. When you do this dot dot dot, I was wondering about that. When you do the dot dot dot, you only do 2. You don't do 3. So I'd put 3 in. So you just put 2 and you just establish the pattern. Start again here. So you just do 0, 10. That gives you the increment. Control semicolon comma 350. I think this will do it. There we go. So pretty handy, right? So because you don't want, if I wanted that, I would not want to do 36 math lines to come up with that. And so I think they're a little too long, so I'm going to do this. I'm going to go 0.95 to 1.05. And that's feeling like what I wanted, suppose. Those are the lengths that I wanted. Okay, any questions on that? So this is the idea of repeated element. You can keep graphing. You can graph something that's has a pattern to it, okay, and in one command line rather than 30 math lines. Any questions on that? Okay, so then the next thing is piecewise functions. So we know that functions you can do, f control x and then equals, whatever, x squared minus 3. Okay, so, and we can restrict the domain, but we can also graph piecewise functions. So like right now on this function line, if I hit control A, that's not where I wanted it. So I need to start over here. So f of x equals, if I do control A, that just makes it a piecewise function of 2 pieces. And if I keep hitting control A, every time I hit control A, it gives me another possible piece to my function. All right, so here's what we do. We're going to say we want f of x to be x squared, or no, let's say 1/2 x minus 3. And so then you can write if what? So the idea of a piecewise function is for different parts of the domain, you're graphing a different function. So let's say this is from -2 to negative 0.5. Okay, so did it graph anything? I don't see anything. So what's wrong?
Is it because you have 4 in the same
What's that, Richard?
Piecewise function.
Nice and
Is
loud.
it because you have four missing functions in the piecewise function?
It's not. I don't think, because it didn't give me an error message. So usually, you know, it'll. Maybe. Let's see. What is this? So I don't see. Let's see. Oh, well, of course. Why didn't it graph anything? Okay, because all we've done is define or try to start defining a function, right? Defining a function doesn't graph it. We've seen that before, right? To graph it, you need a y equals f of x, right? Now what? So now it says can't graph equations with question marks, as if I put the question marks in there, right? So GC's giving the question marks. So yes, we need to finish it up. So we got 1 half x minus 3 between -2 and -0.5, and then say we want x squared if -0.5 is less than or equal to x is less than 1, and then, who knows, square root of x minus 3 if -1 is x is less than 2, and then -5x plus 4 if 2 less than or equal to x less than 4. And let's just get rid of this last line. Okay, so now I have this piecewise function. If I graph it, we should get it. So zoom out. Let's reset the graph. So if you go to graph, you can reset your graph. There we go. Let's zoom out a little bit more. Okay, that's better. All right, so what is this? So what's going on here? And what happened? Oh, that's not going to work. I put in. So what happened? So first of all, is observations. So there's lots of things to talk about here. What do you notice?
That exists between the interval of x equals 1 to x equals 2.
Why not? Why doesn't it exist?
Because the function isn't defined within the function.
Yeah, right. So I tried to define a negative square root, and so it said, nope, can't do it. Didn't show me anything. What else?
The functions are all kind of like connected.
Okay. Kind of connected. So what about this connection here between the line and x squared? Talk to me about that. Is representative? Is it representative of this function?
Wait, so does GC just connects the two functions? Because there's no like x equals equation that represents that line.
Right. So I mean, so exactly. So we got to -0.5, and we transitioned from this line to this parabola, and it gave me a vertical line. What do we think? Is that right? So what about this vertical line? Is it correct? Donna's giving me this teeny little shake of her head. So talk to me, Donna. So why? What are you thinking?
Since it's like a straight line, I was thinking it's showing that the function's like undefined.
Undefined? Well,
But
it's
maybe
defined
that's
all the way up
just
to
like-
negative 0.5, and then starting at negative 0.5, it's defined. So it's defined for all values through there.
If that was slope, it would be undefined though, right?
Oh, right. Okay, it's true. Is this part of the function that we defined? Ashley, a bigger shake. Tell me, Ashley.
I don't think it's like part of the equations you wrote.
Right. So we just have this line, this oblique line with a rate of change 1/2, and then x squared, right? So what's going on here? Why does it show this if this is nothing to do, and it's actually making it not a function, right? It's like taking this thing that we did, a perfectly valid function, and graphing it as not a function. And it's giving us something that we didn't tell it to. So what's happening?
Is it trying to make it like continuous there?
Yeah, so does GC plot all the points? How do you think GC plots? Do you think it plots, how many points are there on this line?
Too many to count.
Infinite, right? Does it plot every one of those points? No, what does it do? What do you suppose it does?
If it's a line, it plots probably the beginning and the end.
Okay, possibly. What about this? Let's talk about this parabola then. How does it plot this parabola? Does it plot every point? No, it doesn't plot every point. So instead, to give us this nice curve, what would it do?
Does it have anything to do with the Taylor series by chance? Kind of.
It may be using a numerical method to generate points, but the point is that it doesn't plot all the points, but it shows us a smooth curve. How would it do that? How would it show us a nice smooth curve without plotting every point?
By plotting enough points
And then doing what?
and connecting them.
Connecting the dots, right? So it's going to plot just enough that are close enough together to fool our eye, right? To fool our eye to see it as curved, and then connect the dots. So what about this? What's happening? In light of that way that GC plots graphs, what do you suppose is happening here? That it's introducing this thing that makes this not a function, and that we did not bring into the mix here. We never defined that, and now it's showing us something that's like a vertical line.
Is GC just thinking like, oh, there's two dots there, might as well just connect them?
Right. So the way that GC graphs, we just said they connect the dots. So it's connecting the dots. Say what every 0.1, not 0.1, every 0.01 or every 0.05 or something like that. It's plotting a point and connecting the dots. So it had a point down here from this line, it had a point up here from this parabola, and it connected the dots. So there may be some different remedies. If we want to see the right graph, what could we do to kind of trick GC into showing us the graph that we've defined here? We need to kind of do something different so that it appears the way we wanted it to appear. What might we do?
Can you get rid of the less than or equal to?
Yeah, generally. So I don't think that will work. Like, we could try that. I don't think that will work, but that's the spirit of what we need to do. Okay, so that didn't work. But so what's kind of the next kind of a little more what am I trying to say? A little more severe step that does the same thing as that.
The new equation that that says x does not equal -1/2.
Okay, and so how could we do that just in our ranges?
Can you change one of the values?
Uh-huh. Like how?
So 1 is like -0.4.
Yeah, that's gonna be too big of a gap though, right? So I think even like 0.49 will do it, or 0.499. Nope. So 0.49. So we're kind of tricking it into doing what we want it to do, which is show that there will be a jump and it will not be connected. Okay. All right. So that's a piecewise. That's a piecewise function. And so, one more feature of this is, say I wanted, let's see, at 0, say I want to take this all the way to 0. So 0.01, say. All right, now suppose I wanted to start, I want this to now connect, right? So I want the start of this parabola to start off where this one ends. Okay, so if I come in here and I do less than or equal to 0, yeah, so suppose I have like something crazy here, like 0.49869 x minus 3.014. All right, so and I want this to come in and start exactly at the point where the line leaves off, right? So I want this parabola to come in and start right where the line leaves off. How can I do that? There's a slick way, because now in this line we've defined what the function is at 0. Oh, let's see. Anyway, yeah. So no, let's go back to 0.5. What did we say? 0.49? And now I'm at 0.5. That's great. Okay, so I want this. I want to attach this. What happened here? 0.51. There we go. So I want to come down and I'm going to attach this parabola right to there, so that this line comes and then the parabola starts up right at that point. Okay. Notice I've defined x to be, when it's equal to 0.5, this is the value of the function. So what can I do here? How can I change this so that when I replot it, that parabola is going to attach right onto that exact same y value right there? I can do something really, really simple to this x squared function. Any ideas?
X squared minus f of 0.5.
Okay, x squared minus f of 0.5. Did it work? Well, it gave us something. That's good. So GC is recognizing this as a valid value in this next line based on the first line, right? So based on the first line, all these points greater than 2 up to and including 0.5 will give valid values of the function, and I can actually use that using function notation in a subsequent line. Did we get what we wanted, Richard?
Definitely not.
And if not, so what happened?
It shifted up
Mm-hmm.
by f of 0.5 units.
Right, because what was f of 0.5? What kind of number was that?
That number right there. crosses. Yeah, like negative 2.7.
It's negative, right?
Yeah.
So it already is negative.
So that just added it.
Oh, brother, what happened? What is happening here? Why is this not working? X squared plus. Oh, right, because x squared doesn't start at that. So we need to do what? That's why I had it at 0. Because x squared isn't 0 at 0.5. So I think we need to subtract. We need to subtract 0.5 squared. There we go. So we needed to get rid of the upward progress that x squared had made over that 0.5. And then to join it up, then we're going to add where this one left off at 0.5. But the point being that in these piecewise functions, you can use function notation. Okay, you can use function notation. But it has to be for something that's been defined previously. Okay, or defined somewhere else in the piecewise function. I can't do f of 0.75. Why can't I do that?
Is it because it wasn't defined in the previous line?
Yes, more specifically.
How does f of 0.75 exist if your domain is including 0.75?
Yeah, do you see this kind of like a loop? Like this is like an infinite loop. Like it's trying to. This is what would define f is 0.75, but you're using it in order to do it. So that won't work. So you got to make sure if you're drawing on the function in a piecewise function, it can't be from the same line, right? Or you're stuck in an infinite loop. Okay, so questions on doing repeats or what is this? Piecewise functions. Okay, so I promised you to show you something I use the morphing operator for, just to keep you thinking about that. So I think it's called this. There we go. So here's something I made to help teach radian angle measure. And so it's to show that the radian angle measure comes from the radius of the circle. And so part of that was, so this is highlighting the radius of the circle. And so then by grabbing this slider, I can peel that radius off, maintaining its length, and wrap it on the circle. And then that will denote 1 radian angle measure, because that's 1 radius of arc length on the circle. So to do this, I used the morphing operator, and in fact I used layers of it. I'll show you the command line. I used it, kind of gets complicated, but I used the morphing operator even nested within itself to kind of get this effect of pulling the radius off its normal position and wrapping it on the circle to teach about radian angle measure. I think I did this for 3 different circles. That's too small. So let's find these bad boys. It took me a long time. So here, was this before I knew about the colon, the control colon or control semicolon to do a, generate the list. I was typing them out all by hand. So let's see. Here it is. So here's this thing that takes it off the normal place and wraps it up on the circle. So I actually used it, I think, 3 times. So first of all, I used it as this point times 1 minus R1 plus A times this thing R1. So the whole structure of it is the morphing operator. Do you see that? There's the 1 minus R1 and R1. But then within this point, this point is x coordinate and y coordinates. Within that even, I used it, right? So here it is in the numerator, and then here it is again in the denominator, in the squared term. So that's too complicated to unpack right now, but I just wanted to show you an example of how I've used that morphing operator to generate this thing that I used, this didactic object that I used to teach about radian measure. Okay, so any questions on any of that stuff that we talked about so far? Okay, so let's, we talked about lines, linear equations built from constant rate of change, and then we talked about those 3 basic principles, right? And I told you these were like the underpinnings of calculus. Do you remember the 3 basic principles that were underpinnings of calculus? Remember this? Anyone? Remember one of them?
Is the first one like change in y equals m times change in x?
That's definitely one of them. Constant rate of change. It's not a crock, right? It's not a crock. Okay. What else? So we had 2 other similar kind of equations. They all have to do with changes. They all have to do with a variation in a quantity.
Is it x final minus x initial?
Right, so you can calculate a change in a quantity by x final minus initial. And then what was the last one? Remember the last one? It's actually kind of a variation on this.
So change y? I mean, is it y? Y initial? Plus change in y?
Right, remember this? And so, and we had said before that this is like these are the 3 most important building blocks of calculus. These 3 little ideas right here. Okay, so let's build on that and start working towards understanding how these build up calculus. So I've got a slideshow here that we can work through. All right, so let's start with a refined meaning for dx. So our refined meaning for dx will be, now we've simply said it was like a variation or a change in x. So now we're going to qualify to say that dx is a little variation in x. Okay, it's small, a small variation in x. And so as such, we call it the differential, a differential. Okay, it's still a variable. It's still a small change that varies, okay, but it's small, okay? So for related variables y and x, talking about differentials dx and dy, that implies constant rate of change. So when your dx is small enough, even with a changing rate situation, when dx is small enough, the implication is that you still have constant rate of change on that micro level. Does that make sense? And so then what would be true at the micro level? Now, if dx is small enough, what would be true? What mathematical relationship would hold even if we don't have constant rate of change, as long as we look at small enough variations in x and y?
dy equals mdx.
Right. So dy still must be a constant multiple of dx, which is dy equals mdx. Okay, so let's flesh this out here. Let's go back to Usain here and talking about speed. And we said that Usain, let's see. We're gonna skip. Okay, yeah. So he broke the all-time record in the 100 by finishing 9.58 seconds. So how fast did he run a mile per hour? We're gonna skip over that. Did he run at a constant speed for the entire race? Yes or no? No, right? So no. So he had to accelerate at the beginning. Actually, the peak speed is kind of before the finish line, and then these sprinters actually slow down just a little bit right before the finish line. Okay, so we want to talk about what does it mean that at 1 second after the start, he was running at 13.754 miles per hour. What does that mean? That at 1 second after the start, he was running at this speed. Anyone want to give a shot at that? And so the question is to kind of pinpoint your focus on what I'm getting at is, what does it mean that at 1 second, he was running 13.754 miles per hour? So let's suppose that's right here. Is that possible? Is it possible that at 1 second he's running 13.754 miles per hour? Why not?
Because speed is calculated based on a change in time.
Excellent, right? So yeah. So in fact, what I'm showing you right here in this picture is, so is he moving? Right there? In that picture?
No, he isn't.
Isn't he going 0 miles per hour in that picture?
Yes.
Right, he's not moving at all. And the problem is, the reason he's not moving is exactly what Donna said. Speed or rate of change requires a little bit of change. Okay, but now we actually zoom in on this picture. What do you notice about the picture? Do you see me zoomed in or not? No, that's just on my computer. So how can I zoom in so you can see it's zooming in? But if you look closely, what do you notice about the picture of these runners?
Their feet are separated.
Well, that's true.
Gosh, I'm scared about the resolution of this image.
I guess you can say they're all like pretty blurry.
Yeah.
Because that picture is captioned
Right.
or captured when they're all moving.
What's that?
I said the picture was captured when they were all moving, so
Yeah.
it's not going to be like focused on them. They're going to be blurry.
Right. They're going to be blurry. So what does that have to do with our conversation here? So does this picture show that he's running at 13.754 miles per hour?
I guess you can say yes, like it was calculated by taking a small change.
Right. Yeah, so the fact that the picture is blurry now, we can come back to this picture and say, oh, we can talk about him running, that he's actually running at a positive speed here because the picture's blurry. The picture represents a small variation in time and the small distance that he ran in that time. So 13.754 means given some change in time, right? Given some change in hours, what?
Would you say that, like, given that time, like, over that period of time,
Mhm.
he travels that 13.754 miles per hour at, like, at that speed?
Okay, but we're trying to define that speed, right? So we're trying to define that rate of change. So given that time that the shutter was open, what can we say?
His instantaneous rate of change was 13.754 miles per hour.
But that sounds like...
Right, that's probably not the direction.
Yeah, so but instantaneous rate of change goes back to this idea of freezing time, right?
Yeah.
Saying at 1 second. So really what we have here is like a small variation in time from say 0.995 to 1 or something like that. So what is the meaning of this rate of change? Given a small variation in time, what can we say?
Small variation in time, Usain Bolt runs 13.74 times as much as that small variation in time. He travels that much.
Right, exactly. So the change in his variation in distance, call it dy, is going to be 13.754 times whatever variation in time we have. Now we have small variation in time, right? So because there's a small variation in time, we can assume constant rate of change, right? Constant rate of change, even though he's accelerating at this moment, right? In the first second, so for the first couple seconds, or maybe the first half of the race, his speed is constantly increasing, right? It's increasing, but with a small enough variation in time. For instance, the blur of the blur, or the small enough time represented by this blur, we can assume that for that little amount of time, his change in distance will be 13.754 times as much as that change in time. dy equals mdx. Now, what if I set a dx of 2 seconds? Does this work?
I would say no, because that's like not that small relative to this situation.
But what's the problem with it not being small, right? So you're right. So I cannot use dx equals 2. How come?
Because it's not kind of building off what Richard said. It's like too much time. It is a constant rate. That's going to be hard to calculate, like a constant rate.
He's not going at a constant rate of change.
Right. So like as soon as half, or even half a second, or maybe even less than half a second goes by, now his rate's different, and dy equals mdx assumes a constant rate. That's why we need these small variations. Okay. All right, so how fast is he running at this value of time? 0. He's not moving. But what we want to talk about is at the moment, right? When the moment of 1 second has lapsed, how fast is he running at this moment in time? So a moment is a small enough variation in time that we can safely assume a constant rate of change and use dy equals mdx. Does that make sense? So a moment is a small enough variation in your independent variable that for dx's within that moment, we can assume dy is mdx. We can assume a constant rate of change for that whole moment. So a moment is a small change in the independent variable. Dx is not equivalent to a moment. It varies within the moment. So dx is even a smaller variation than the moment. And any variation of dx within the moment, we can assume will have constant rate of change with the corresponding dy. Okay, so does this concept of moment versus dx, the difference between moment and dx, does that make sense? Or anybody have a question? Okay, so then the rate of change in a moment exists if there's a small enough interval in which the rate of change is essentially constant. So for all our practical purposes, a moment is a small enough change that we can assume the rate of change is constant, and then we can use dy equals mdx within the moment for varying values of dx. Okay, any questions? Oops. So this value, 13.754 miles per hour, that's his constant rate of speed at the moment 1 second into the race. So there's a small variation in time around 1 second that we're assuming he's traveling at this rate, a constant rate of 13.754 miles per hour. So therefore, given any variation in time in that moment, his corresponding variation in distance will be 13.754 times that variation in time. Okay, so the function f relates Usain's distance from the start line, the dependent variable, to the time since the race started, independent variable. The displayed graph of f near x equals 1, so that's right here. Here's the graph of his distance versus time. Is essentially linear from 0.99 seconds to 1.01 seconds. Imagine x increasing from 1 second to 1.006 seconds, and simultaneously his distance from start changes from 3.4882 meters to 3.5251 meters. Okay, so first we're going to say, what is Usain's speed at the moment x equals 1? How would you calculate his speed at the moment x equals 1 second? Elizabeth, do you know how you would do that?
I'm not like 100% sure, but like, so our x is increasing in like seconds, so that's like our change in x,
Okay,
right?
good.
And like our distance is changing by like the meters, so we have to like find like how that's changing linearly to find like the relationship between them, right?
Okay. So just to get the rate of change then, how could we use this information to get his speed?
So we like subtract the final like meters from like the start from like the initial meters from the start, and like divide that from like the change in time, right?
Right. We're going to take the 3.5251 minus 3.4882, that's our variation in distance, divided by, what will we divide by? What value will we divide by?
Are we dividing by 0.006 seconds?
Right. We're going to divide by the variation in time, which is the 0.006. Okay? And so here I'm showing you the moment. The moment from 0.99, so it's the same graph, but now I've zoomed way in to show you between 0.99 and 1.01. What do you notice about the graph?
It's essentially linear.
Yeah, right. So now I've zoomed in on a small enough piece of this one over here to show you that it's essentially linear. And so this is kind of it's appropriate to assume constant rate of change. Okay, and so then within this moment, we can show changes in y varying in proportion to changes in x. And specifically at 1.06, which is at the end here. Oh, thought I had it. Shoot. Oh, there's too much here. Jeez. Oh my gosh, it's killing me. Pause. Here. There we go. Okay, that's what I wanted. So now I'm showing here specifically at what, from 1 second to 1.00 seconds, the variation in time, and the corresponding variation is in distance, and we have proportional, these changes are in proportion to one another, like constant rate of change. Okay, so we have an exercise here to make sense of this problem using symbols and values. Okay, so for each of these 6 items below, we want to identify the value associated with that item, and then how it's represented symbolically. Okay, so we're going to make a chart here. So values for each of these, and then symbolic notation for each of these, and then how you would represent it on the graph. So how you would embellish or add marks, symbols to the graph or for each of these items as well. Okay, so I think what I'll do is we got 10 minutes left. So is there anyone, I'm going to open up a breakout room, and just for one student at a time to answer any questions you have about the project that we have due Thursday. So does anyone have their hand raised? You want to go first because you have burning questions about Thursday.
I volunteer.
What's that?
I have a question.
Okay, Richard's first. So hopefully when I break him and I go out, you'll still be able to see this in the main room, I hope. So I'm going to try. This is about putting everyone in breakout rooms. How do I just make one breakout room? Anyone know how to make just one breakout room?
Maybe you make all the breakout rooms and then everyone just leaves immediately.
Yeah, but yeah, I can't have the main room. Okay, so let's just forget this. All right, let's just talk through this activity here. And we'll skip the breakout rooms. And then in terms of questions, I can stick around. Oh, I can't. I have office hours today from 2 to 3:30, or you can please make an appointment with me. I have free time the rest of the day after office hours. So if you want to make an appointment with me to work on your, to talk about and get help with the project, or if you're smooth sailing and the project's going fine, then we don't need a consultation. Okay. So let's talk about this here. So the initial value of the independent variable. What is that value? I'm just going to go right down the line here. Angel. So in this situation, what's our initial value of the independent variable?
Is it 1 second?
He wants 1 second. It is. Okay. Symbolically, how do we symbolize that 1 second in this situation? So Ashley.
X.
Okay. So is it any x or a particular x?
Particular X.
Okay. So how would we?
DX maybe.
So is it a variation in x?
No, it's 1x. So
Mhm.
I don't know.
So which x is it?
Yeah.
Which x is it?
Could it be the start of the horizontal line?
Initial or X.
Yeah, x initial, right? X initial. Okay, what's the initial value of the dependent variable? So Sarah. Sarah, are you there?
Yeah, I am.
Okay.
I'm like, with the initial value of the dependent variable, isn't that the 3.4882?
That's right. And then how would we represent that?
initial.
It could be y initial. And so remember that this is this distance time function is function f.
So it'd be f of x initial, right?
F of x initial.
Oh, okay.
Just f of 1. Yeah, good. Yeah, so f of 1, right? F of 1. All right, what about the differential in x? What is its value in this situation? Donna?
0.005.
Close enough. 0.006.
Oh.
Yeah, so yeah, you got it right. Just little numerical error there. Symbolically, how do we represent that symbolically?
Would it be f of... Wait, no. Is it x final minus x initial?
It could be, but we got a better way to do that. So yes, it is. It could be x final minus x initial, which is equal to what?
Like, do you mean like 1.006 minus 1?
But this is symbolically now, right? So no values. So yeah, x final minus x initial is dx, right? It's dx. Okay, the differential in f. So Elizabeth.
I can't do math that fast.
Okay, well tell me what you would do.
525 minus 3.48.
Good. Yeah. So it's gonna be exactly. That turns out to be 0.0368. And how do we represent that symbolically?
Would you say like df or the
Yeah, this is a little bit shaky notation, but it's kind of the best we got here. So we're going to do df. We know that f is not the variable, right? F is the name of the function. This is kind of like the best we can do. All right, what's the moment in question? What did we say the moment in question was? Where's Richard? Richard.
The moment is like the small enough variation in time so that we can assume constant rate of change.
Yep. So what did we assume in this situation as our moment?
0.99 to 1.016.
Right. Yeah. So it's like this whole span of the x-axis here on the right graph. Okay. There's no really symbol for that. It's just it's a interval notation. Okay, Yasra, what about the rate of change at this moment? What is its value? Or if you can't do it in your head, what would you do to get it?
0.0368 divided by 0.006.
Very good. And what symbol do we use for that, for the rate of change? Yep. Or df dx, right? So df dx or m. Okay, so what are we doing? So we computed some answers along the way, but really this activity is about modeling the problem, right? So taking the information, understanding our terms and what their values are, and then modeling with symbols. So this is, when you have real-world contexts and you're teaching your students, you really want to train them to get out of the mindset, the calculational mindset of what are the values that I'm going to get in the problem? What are the formulas I'm going to use and to get an answer, right? Rather, let's start the problem by kind of like unfolding the information and representing it with symbols. Okay, so we got a little time left here. So let's do this next screen. So here's similar but different. So it's the same function f. And his speed at the moment at x equals 0.4 seconds is 3.05 meters per second. So I'm now giving you the rate of change and the starting distance, and we're interested in what's happening at 0.408 seconds. So what is the moment in question? What's the moment in question? So we could pick off, say, from 0.4 to 0.415 or something like that. All right, and so it's just kind of like, and there's kind of more than one right answer with this, but it's any small enough range of time in which we're considering this constant rate of change at 0.4. What is the rate of change at this moment? So that's our df, dx, or m, and that was given in the problem, 3.05 meters per second. Key values of the independent variable would be starting x initial and x final, which would be our 0.4 and 0.408. So what's the differential in x? Quick, so we can get out of here. Differential in x is?
dx.
Dx, its value is?
0.008.
0.008. Excellent. Differential in f. Okay, so there's two ways to symbolize this, the differential in f. We could do df, or we could do what? This is the variation in distance. How could we show that symbolically?
dy.
Okay, but
F final.
yeah, so df or mdx, or yeah, f final minus f initial. But this is really the way we're going to get it, right? Because we don't know what f final is. So since we don't know what f final is, we're going to use mdx. Okay, and so then we're going to multiply our 3.05 times our 0.008. We're going to get 0.0244. His initial distance from start is f of 0.4. And the value is 0.702, which I gave you right here. So what about the final? This is the kind of the big conclusion here. Final distance from start. What are two ways to represent that symbolically?
F of 0.4 plus df.
Good. All right, so f.0.4 plus df. And is there another way to represent that?
Just f of 0.408.
Good. Excellent. So f of 0.408 equals f of 0.4 plus m dx. And if we have all those values, we can crank it out, right? So we have the f of 0.4, we have the m dx, and we can add them.